Hi everyone, I'm Meraj. I'm a PhD student at The Ohio State, and I work with the Interactive Data Systems group, which is led by my advisor Arnab Nandi. And despite the introduction, this talk is not about time travel. So a quick overview of this talk. First, I'll go through the motivation behind this work, which is how do you enable interactive data exploration over large data volumes. And then I'll walk through very high overview of existing solutions, a classification of the existing solutions and techniques. And then I'll present typical user interaction behavior and typical characteristics of certain user interaction widgets that the current techniques do not utilize, and how we actually exploit those to come up with better prefetching and caching strategies. Then I'll present the performance evaluation for the system, and I'll end the talk with the takeaways and a brief discussion of future work. So the motivation behind this work, data-driven analysis, the entire process, has pretty much become a lot about ad hoc explorations. And this has shifted the traditional database interaction paradigm from the question answering style of interaction, where users used to basically submit a single SQL query, then wait for the result. Now you have interfaces like maps, range sliders, and you basically are issuing queries almost at the rate of screen refresh, which is a lot. And if there are multiple clients connected to the backend, this can overwhelm your database. So the idea is to have this caching layer, a middleware, buffering the database from this sort of workload. So it's kind of obvious that an interactive interface, which updates in real time, is kind of a hard requirement for ad hoc explorations. But then users generally prefer interactive visualizations, even if it does not really help them in performing a specific task. And we always had this intuition. We did a user study to validate it. It was a very simple task, a pre-specified date selection. You just had to select a date range. And we had 3 different interfaces. The first interface was basically just a from and to date text input box, but you also had associated calendar widgets with it. So you could just select the dates on the calendar, and you didn't really have to type. The second interface was a range slider, and you basically select the range on the slider. But the associated result, which was basically a histogram, and that result was not updated until the user was done performing the selection, or they could explicitly issue the query by clicking a button. And the third interface was an interactive interface where when the user would move the slider handle, the visualization would update in real time. And we employed 24 users, divided them in groups of 8, and to each user we showed 2 of these interfaces. So the first one is the interactive version, which basically updates in real time with the slider handle movement. And there was a clear preference for it. We also measured the task response time, but there was no difference in the task response time across all 3 interfaces. In fact, most of the users completed the task faster with the text input one, which is the least interactive, because they just had to select the date on the calendar, and we set the calendar to the current year, the year that they had to select. So most of the solutions enabling interactive data explorations, you could classify them in these 3 techniques. The first one is query rate limiting, which is very common in web apps. Debouncing and throttling, you basically limit the number of queries which can be issued in a fixed range of time, and you set a minimum threshold between consecutive time threshold between consecutive queries. Or you could prefetch and cache results, or if it's a semantic data cache, you can prefetch and cache data into a cache for the speculated or predicted queries that you probably would issue in near future. Or there are approximate query processing techniques where you would sacrifice accuracy for faster response times. Our work basically uses all these techniques and hopefully can make these better. So these are the two main characteristics which we use. So a typical user interaction behavior, there's some sort of predictable interaction pattern or directionality to it. If there is a fixed axis of motion, like in a range slider, you can only move linearly. Or even if it's a map, you can predict the direction. Even though there are prefetching techniques which actually exploit the directionality of the motion, none of them actually use the query rate, how fast the queries are generated or how many queries are generated in a specific interval of time, which we do. And there are certain UI widgets now which have inherent physics associated with them. So you have controls which basically simulate friction, inertia, springiness, like most smartphones scrolling a list. Just a quick flick initiates the list, and without any further interaction from the user, the list accelerates very quickly, and then it starts slowing down gradually. And it's a very gradual motion, as if it's sliding under friction. So the main part about that is that's a simulated motion, and you can predict that entire motion at the very start of the user action. So for example, this is the top image shows the range slider handles ghosted out trace at every 100 milliseconds for a fixed range selection. So if you see at the very start, the traces are separated far apart, which means the queries are being issued at a very high rate. And then it slows down towards the goal query or towards the target. And the bottom image is basically showing the displacement over time. So at the start, the queries are being generated at a very high rate, that basically being the point. And this is a displacement over time trace for a range slider which simulates friction. And if you notice, this is a very perfect power law decay of the velocity over time. And you know this at the start of the action. So you can probably utilize to design prefetching strategies. So how do we use these? First, the first technique, interaction rate aware prefetching. So once you know what's the rate of query being issued at any instant, how do you use that? So for most prefetching techniques, it's after a cache miss, you prefetch certain number of query results or a fixed range of data bound. But if the queries are being issued at a very high rate, it would cover a larger data bound in a shorter time compared to queries being issued at slower rate. So for high-speed interactions, you should ideally be prefetching larger data bounds. Similarly, when the user is issuing queries at a very high rate, so like the case of range slider, the initial interaction, the user is basically just zipping through a very large portion of data. So they are probably not interested in it, and they are not waiting enough to observe the feedback from the system. So that could probably mean that you can relax the accuracy constraint for those queries. And finally, the physics-aware prefetching and approximation. Any widget which has this deterministic physics associated with it, and you can determine the entire motion at the initiation of user action, you can generate the entire workload, the query workload for the session at the very start and issue it to the backend. And that's what we do. So this is an overview, a simplified overview of Flux Capacitor. A query comes in from the UI. It is annotated with its motion characteristics, basically what speed the interaction rate is at that point. And then we have a client-side query processor, which basically keeps checking the front-end cache for, it's a semantic data cache, so it checks what data bounds it is currently maintaining. And if the front-end cache doesn't have the required data extent to answer the query, it would issue a partial data query to the server. And this is all aggregated at the front end, and then it issues the result to the UI. The motion analyzer part, it is clubbed with the debouncing and throttling logic of the interface. So basically, that's something that you are doing anyway, so there's no additional cost to it. And I'll present the performance evaluation that we did for this. The data set is the 3D road network from UCI machine learning repository. We used this because the workloads that we used for performance evaluation, those are traces from one of the previous works by my group. So we already had range slider query traces from a lot of users. And the metrics used for evaluation are data stalls, which is basically the time when the UI is stalled for waiting for a feedback from the backend, and how many times the UI stalls. So whenever the UI stalls for data, that's basically shows up as lag for the user, and how long are those data stalls. And the second, the latency, the average query response time. So the first workload is a timestamp sequence of queries generated from the selection of specified latitude and longitude range. And the front-end cache is an R tree. And the baseline setup we use for evaluating our interaction rate aware strategy is a simple directional prefetching strategy. Now, with most directional prefetching strategies, you prefetch a certain fixed range of data on a cache miss. Here, we chose to prefetch 5% of the entire data range on every cache miss. Now, that's not exactly arbitrary. We tried out multiple fixed ranges, and longer ranges would lead to longer data stalls because those are larger data bounds, and it would take more time to, the network latency would be higher. And if we reduced that data range, it would just lead into more stalls. So the interaction rate aware prefetching strategy basically leads to fewer stalls, 2 compared to the baseline setup of 5. And the stall time is almost half of the baseline setup, which leads to the overall interaction time being shorter. Now, for the physics awareness study, we did not exactly have traces from users. And that's also because we are studying this arbitrary flick of the slider handle. It's not a specified range selection. So we have 3 different setups. The first one is exact caching, where we are not approximating the results. So this is basically the interaction rate aware prefetching cache from the previous results. The second one is the approximate caching setup, where we process the queries on different sample rates. So for queries which are issued during high-speed regions, they are processed at a lower sampling rate. And queries which are really close to the goal query, they are processed on the entire data. And lastly, the physics-aware prefetching basically generates the entire query workload at the start and uses sampling and prefetching. So basically same as the last one, but you know the entire workload at the start of the session. So if you notice, the physics-aware caching basically performs the best of all three setups. And it has the least variability in query response time for individual queries. And each of the queries is pretty much under 100 millisecond, which is generally considered to be interactive response time. So takeaways from this work, interactivity in visualizations is preferred even when it doesn't really help the users in performing the task. In fact, it might even take them longer. Interaction rate-based directional prefetching generally performs better than fixed range directional prefetching. And you can use this with other prefetching techniques too. Like, it does not have to be directional prefetching. If you knew how the interaction pattern is, you can still use the query rate. And UX widgets with certain physics metaphors have deterministic behavior, enabling generating the entire workload at the start of the user action. Future work, so we have quite a few approximate query processing systems now, where you can specify the error bounds and the latency bounds. And Flux Capacitor can be used to model those constraints for those systems. And there are quite a few data summaries which support incremental addition, refinement, and deletion, which can be used as the cache instead of the R-tree or the sampling techniques that we used. And some of these characteristics or strategies that we used for rain slider, the results that we presented, they would directly translate to other interaction techniques such as panning on a map. And since we are using approximation techniques, if we were to include this in a visualization stack, we need uncertainty visualization techniques, which there are a lot of available. And finally, this is something which is under review, a data platform for shared augmented reality. It basically has a local client-side cache, and we use prefetching and prefetching based on localization and path prediction. So some of these would also apply to that. So that was it. Thank you for coming. And if you have any questions, I can answer them now.
We have about a couple of minutes for questions, so one or two quick ones. Right, I can start again. So I'm not sure, maybe you said this, I missed it. What was the platform on which you performed the experiments?
Oh, so these are all web visualizations. So
correct.
Basically, the entire code is JavaScript.
No, so it's not in terms of the code, like as an end user, was the end user or the participants, were they using a mouse versus were they using touch?
They were using a mouse for the rain slider
okay.
selections. Yeah.
So especially because you're talking about physics-based,
Yeah.
features, how do you think it changes when you actually use touch, where it's much more prevalent in terms of how the inertia works or how the velocity
Yes,
works?
so I actually do have preliminary results from panning a map on touchscreen.
Right.
I haven't included it in the paper because I'm still working on it, but it's basically, so this is the directional prefetching strategy that I'm using. So it is basically what you would expect it to be, because the physics does not actually affect how you are approximating the speed bands. So the prefetching region, it doesn't matter if you have inertial motion or if it's just on the basis of the user's interaction.
Okay, we can talk more about it offline,
Yeah.
but I think
I'm just checking if I have
are there any other questions? I just want to make sure I give the audience a chance.